Eric,
Hey Charles,
how you doing, man?
I'm doing good.
Excellent. So we are in,
We're in building 42,
Yes.
where I used to be a long time ago. And we're talking with Patrick Dussud.
All right.
Hi.
Hey, Patrick, how you doing?
Hi, good. How about you?
Excellent, man.
And so Patrick is the kind of man behind, the magician behind the garbage collector in .NET. So first I wanted to ask him, can you explain to us what garbage collection is?
Sure. So if we start with the basic and we start from a non-garbage collected language and we'll contrast. So when we take C++, C++ has a new operator and you call new to allocate all of the objects that have an extent that is beyond a call. So in C++ we have automatic variables which are allocated on the stack, and their lifetime is the extent of the call. And then we have some that we want to keep longer for an indeterminate amount of time, and the programmer will decide what this amount of time is. So they create with a new, and then when they believe that this variable or this storage is not relevant anymore, then they call the operator delete on it. And they need to pick the time themselves, and there are pitfalls with it. In particular, they may not know when the storage is up for reclamation because they may have passed it to other module, and that module could have kept a reference onto it. So that in general, unless you have a complete visibility as a programmer, a complete visibility over all of the ways that the storage that you just created can be used and passed around, then you are in a heap of trouble, as I can say. So garbage collection or automatic memory management is a collections of techniques to take on this problem and relieve the programmer from the knowledge of when to destroy the storage that you created yourself. So a automatic memory manager has an operator new but no delete, and the delete will be done at an opportune time and safely, so only when the storage isn't referenced by the program anywhere, then you can reclaim it. So that's the basic of automatic memory management. Now, how do we do it?
Yes. So how do you know what is garbage and what is not?
Exactly. So we can actually get back from first principle. How do a piece of memory can be referenced? So in order to be referenced, it means that the programmer needs to be able to, by following a chain of objects or a chain of reference, be able to get to it. So what do the programmer deal with? Well, he deals with variables. And variables are either on the stack, the automatic variables that I talked about, or global variables or static variable. Let's call them global for the sake of this argument. So if there is a chain from a static or a automatic variables or chain of references to a given storage, then it is referenceable, therefore it should be kept. Inversely, if there is no chain, then you lost this area of memory. You cannot get it back because you cannot, using the tools you have, which are variables and references, to get to it. So how do we mechanically make that to work? Well, we have to have a mechanism to explore every global variable, and hopefully see the linker, for example, knows where the global variables are, and then we need also to enumerate all of the variables that are on the stack. And for this, usually it's a combination of the compiler that laid out the variables and registers, by the way, and registers because variable could be optimized into registers. So the compiler lay them out, and then the runtime needs to know how to work the stack. And so this part becomes a little bit tricky, and that's the first step for a program to be managed. What do we call manage? Where part of it is you need to have a god that knows how to manage the working of the stack while the program is going, or stop the program because the mechanisms need the program to be stopped during that time. So that's the first time in being managed. It's a big step function in runtime services. If you want to do a lot of things that look like .NET but be unmanaged, you can only go so far, and you beef up your library, and then at some point you say, oh, now I need to do automatic memory management, I need to work the stacks, what do I do? And then the complexity goes up by a big notch. And so let's start there. So now we have a runtime that knows how to either stop the program or not, but certainly knows how to start giving the automatic memory manager the list of all the global variables and all of the static variables and all of the stack variables. So from there, you need another piece of magic thing that knows how to trace the references from one object or one piece of memory to the next. So in general, there the compiler knows that too, because when you declare your class and in a static type language, then the compiler knows exactly the offset of each reference within the object. So if it can somehow communicate this to the automatic memory manager, the garbage collector, then the garbage collector can do a complete job of tracing. And by tracing, we mean we go from our variables and we follow each reference all the way to where they can be until we find objects with no references. We take care of cycle in the process because we can't go in an infinite loop, so we have to remember which object we already traced. When we finish the tracing, now we have a map of the truth. We have essentially the collection, all of the storage that are still referenced. And then we can say the storage that was allocated but is no longer found on this reference map, then is garbage. So a collector will somehow trace by various techniques and then will dispose of the memory that was allocated but not traced. And there are various techniques to do that. Basically, two big techniques. One technique combines the tracing and moves the object into another place, so the old place can be abandoned. And those are what we call copying collectors. They are very simple to write. I mean, you can write a copy collector in probably 20 lines of code. I mean, if you it's that simple, right? What it is every time you trace, so you find an object, you move it to another space, and to move, you just move in order, increasing address, and then you set a forwarding bit that says, hey, this object has been moved, and here is where it has been moved. So you do that, and then when you find an object that's already been moved, then you just stop. When you find a new object, you move it, and then at the end, when you have no object to move anymore, what you go into your new space, and you go from the first to the end, and every time you find a reference that hasn't been moved, you move it. And when you're finished, you're at the end of your heap, you're done. So it's extremely simple. The only problem with it is, first, it requires to be tolerant of object moves, and sometimes it's not the case. For example, in the .NET programming, when we call unmanaged program and we pass arguments such as strings, we count the unmanaged bit counts on the fact that the string is not moving. So either you cannot garbage collect when there are calls into unmanaged code, or you have to temporarily, what we call pin, essentially makes this object not movable. So that's one of the problem with a copying collector. The other problem is the fact that we move a lot of stuff. Moving takes energy, instructions, and even takes real memory. So essentially the peak memory usage of a copying collector could be twice as much as your live data, which is sizable. So there are other techniques. So the other techniques are all based on two or more phases. The first phase you trace, and you leave essentially a bit somewhere in the object or on a table, a side table that tells you which objects are already marked, means which objects are live. And then the second phase, you go through your memory store, and then you pick out the objects that are live, and you can compact them or leave them in place and turn the unreferenced memory store into free lists items that you can reuse later. So, and there are various techniques to move object around. The one that I use is called sliding compaction. Essentially, when we can, we just squeeze the space out, and so we end up with a very tidy heap at the end. That, interestingly enough, is also respects the intuition of the programmers that if objects are created simultaneously, very, very close together, then they will be locally together, which is a very good thing to exploit. A copying collector essentially will use various, if you just do the basic one I explained, you'll end up with a depth first, a breadth first, reallocation of objects. So if you have a tree, you'll end up, each level will be co-located, which is not necessarily what the programmers was intended when he created these nodes. So that's the basic of a garbage collector. Now, that basic thing is kind of a, the Model T of the garbage collector. One of the problem with this is that we have to repeat these steps, and we'll end up, you look at your store and say, wait a minute, I have all variable, I have my static are just there, and I'm not disturbing them. I allocated them when the program started, and I allocated a bunch of stuff that I consider to be static data. And why do we have to keep tracing it all the time? And as the heap grows, then the more and more cycles, it's just there to trace things over and over that are known quantity and fairly static. So the idea of ephemeral collection came, and the idea is that generally there is a lot of temporary data. And temporary data means that you create and it dies very quickly. And if we could concentrate our work of most of the work of garbage collection onto the temporary data, we have great success. And the success can be measured by essentially what you trace versus what you reclaimed. So I call that the survival rate. So the survival rate is out of the store the part that you keep versus the part that you reclaim. So if the survival rate is low, then GC is very efficient. If the survival rate is very high, then GC just spun its wheel tracing, and at the end say, yeah, I traced everything and nothing is dead. Therefore, I'll do it soon, but this time there was nothing to be gained. Mm-hmm. So doing ephemeral collection enables to concentrate on the part where there is the least likely survival. And so essentially an ephemeral collector will collect the newly allocated objects and then tenure them or promote them into another generation that is older, and there is various schools of thought of how many generations you need to have. Some of them are based on the mechanism that they use, some are based on the logic, having logical ages such as ours. So we have essentially 3 generations. We have just the generation 0, which is where objects get created. Generally, we have less than 10%. Most programs end up with survival rate there of less than 10%. Then we have a settling generation, if you like. So generation 1 is there to, if you catch some requests in flight or some operation in flight, we have some temporary that appear not dead yet. They are about to be dead, but we don't know that. So we catch, you are on a ASP.NET server and you do a certain number of requests that are in parallel, that are not finished, and you do a garbage collection, you'll get a certain number of requests in flights. So the flight can be because you are on multiple CPUs or because there is latency and a request is composed of multiple asynchronous requests. So you get the request, you parse it, you do a SQL database request. During that time, your thread is being parked. Another request can come in. So you have a certain number of requests that are called in-flight, and they have a data set that will disappear at the end, but as you do the collection, it's there. So this will be promoted to that settling generation and will give additional time to die. And so once in a while, when that generation grows beyond some limits, then we do a collection of what we just allocated plus the settling object that are in the settling generations. And most of the time we find that, what was in Gen 1 now is dead because they were mostly by, maybe 90% of it was data that was caught in flight by mistake, if you like. And then only 1% is actually much more stable data that we transfer into our final generation, most stable generation called generation 2. I did experiment with adding more generations, and I didn't see any gains. And there are more bookkeeping required when we have more generations, so some data structures that we have become less efficient. And so we are actually not gaining but losing a little bit. But again, that highly dependent on the mechanisms that you are using for the garbage collection.
And so you mentioned like the ASP.NET example where you do asynchronous calls.
Right.
Do you see like different programming styles have impact on the way memory is allocated? Like say I'm using LINQ with lots of closures, or I'm using more old school like loops. And
right. If you use old school loops, and there is ways to actually even in C# to try to never allocate. And then there is at the other end, which is functional programming, which is essentially based on copying rather than mutating data. So by mutating, I mean you take an object and then you jam new value into its members. And it's jamming new value into a member of an object is old school, as you know. And one of the problems is, we said before that we don't exactly know where objects will be referenced from, which modules. So when you jam a new value into an object, you may affect another module that took a reference onto your object, but doesn't necessarily expect the value to change. And actually, when you do that, and with multi-processors and concurrency, you have a problem. Usually, you need to lock. And then locking introduces problems because it introduces latency, it introduces non-concurrency. So the new school is functional programming, where instead of jamming new values, you just copy the value into new ones and you just return new values. So that is conducive to actually a lot of garbage and will produce a different workload than the old school Fortran-like workload, where you are going to not allocate anything.
And so how do you deal with that? So
right. So our garbage collector, when I designed it, we said I don't want any knobs, and most system require the programmer to adjust some settings and say, hey, I know I'm in a workload where there is a lot of garbage, so I need to give a little bit more priority to the ephemeral collection. And for us, actually, what we do is we try to be adaptive. So we measure a number of factors that we can measure. We can measure how long it takes to do a collection. We can measure the survival rate. We can measure the growth of this and that, and we adapt to it, and we modify the schedule and the way. For example, we don't necessarily do a compaction if the heap is not compacting very much. So we have internal goals of compaction and of fragmentation, and if they are exceeded, then we'll do compaction. So there is essentially that's where we go from the Model T to kind of the rocket essentially, and there we have a number of mechanisms that are all internal, not really accessible by the user, but these mechanisms are controlled by a policy that tries to do the most efficient collection it can. And by efficient, we mean keeping the heap overhead low. By heap overhead, I mean the size of the heap versus the number of useful objects that the programmer has in his heap, and by also minimizing the CPU times required to do collections overall, and or depending on the intent, and then we'll come back into that, reducing the latency of the collection. So what the programmers essentially in our world has intents. And the first one, which is kind of a big intent, are you server-like or are you workstation-like? So server-like essentially is the ideal case is ASP.NET. It's a process which is MP scalable at the core and tends to execute a fairly uniform set of small operations that are isolated with each other. So those are useful characteristics to work great on the server GC, but they are not absolutely required. So if you stray from these, if you're introducing coupling between your workload, between the independent operation, then you are going to reduce the efficiency of GC, but you're not going to make it kill over. So essentially, the best case for it is something where you have independent requests coming in, and you have no survival beyond just sending the response back, and that's we'll have very good scaling on a high number of processors and very high perf. And then if you introduce coupling, then you'll have to lock. So the intuition that it's bad, and it's bad for GC and bad for your program. So the nice thing about this is the normal intuition about how your program runs is mirrored into how well the garbage collector runs. So that's one of the nice things that we try to do. And so the programmer has to have those two intents. And then in the workstation, we recently introduced a low latency mode where the programmer further say, I care more about latency than percent time in GC. And then there we reduce the latency, and it's suitable for people doing with care, but it's suitable for people doing video application completely in managed code.
Excellent.
Okay, and so one interesting thing is like when you right in the beginning when you explained about the stack, that you have to walk the stack in my opinion, the stack is also kind of some really old school thing, because if you look again at like functional programming, the stack is really more of a nuisance, right? Because everything is allocated on heap and you have a closure.
They actually have like some schemes are implementing their execution stack is implemented on a heap.
Yes, and
which is it's certainly something that can be done, and don't remember which scheme implementation does this, but yeah, they do a good job.
Yeah, and so have you ever kind of thought about doing that for the CLR, because that also kind of opens up other things, right, where you can do continuations and things like that.
We talked about it. It's a big step, and so we haven't taken it. I hope that we will explore that in the fairly near future, but that's something that. The problem that we face is the CLR is a universal engine so far, and we try to execute COBOL, Fortran, C#, and F#, and with Visual Basic, which is very similar to C# in its workload.
Yep.
The other ones are each have their own workload characteristic, and I would hate if we had to say, pick this version of the CLR because you are doing workloads like this, because it's not conducive to composition. What I love about the CLR is that you get people don't have to make a choice about which language they use, and they still compose very well. When you pick an assembly written in F#, you don't have to know it's written in F#, and you can call from your C# and it works well. So we will adopt new techniques as long as we know how to make them perform well for the old school. And that's a little bit of a challenge. That has been a challenge, for example, for us when we did some research, and fairly well advanced research in transaction memory.
Yes.
And that's a very cool, that's also a new school thing. Instead of locks, you use transactions, and unfortunately the amount of for the prototype that we've developed, the amount of overhead that is required even for normal programs, the amount of additional side structures and data that you had to put in the CLR doesn't warrant its use, its general use.
So can
we go ahead.
I was going to say, clearly don't mean to interrupt you, but is there some sense of a transactional garbage collector? So I understand with software transactional memory that was added in the nice dev labs thing, it's actually a different CLR.
Yes.
So they had to do a bunch of work.
Yes.
But my question to you would be, the concept of transactions, could that be applied to managing memory in the sense that you are
could
a garbage
actually
collector?
You could if you can ensure there is no leaks. So that actually it's called Arena. Arena memory management means that you are going to put object into a place that is closed, and then all of a sudden you say, I don't care about this arena anymore, this place, and you can get rid of it.
Okay.
Which is exactly the way SQL Server manages its memory. So SQL Server will allocate, and then when the transaction is finished, just reclaim the pages that it allocated. So combination of, it turns out they leave money on the table because a number of their storage blocks are actually dead logically, not available before the transaction is finished. So in a way they over allocate because they don't know that, so they keep going. And then when the transaction is done, and it's a little bit like us, if you like, if you we would allow the program to run and not collect Gen 0 while there are higher collection in progress, then you leave money on the table because you just allocate, and there is a bunch of objects that should be reclaimed that you delay a reclamation because you are in the previous concurrent GC we had. That's the problem we've had. So you leave money on the table. So taking advantage of of transaction is certainly something that is very useful and would allow to get rid of a bunch of stuff. But I think the fine-grained collections allows you to actually keep your memory very compact and even take advantage of some cache locality that otherwise would be wasted.
So that was one of my other questions. It's like, because we talk about like this high-level garbage collection, but like the machine is very sensitive to cache behavior. So how do you kind of bridge that gap?
So for us, since I explained before, we have an adaptive system. We actually do take into consideration cache size to modify our heuristics and get rid of it. We also cooperate with the OS to know when the memory, the real memory, the RAM, is getting tight. And then we step up and our schedule, and at this point we are ready to waste CPU cycle to avoid the onset of paging. And that's something that we, over the years, we worked on refining, and something that is very still something that we work on, because we would like to have great characteristic up to when we are right on the onset of paging. And usually on servers, people tend to be very conservative about memory. When the memory goes over 60%, they tend to say, oh, now it will be time to replicate our services onto more hardware. And we believe we can consistently get higher than that if we do a good job.
So you can say that you make computing more green.
Right.
Yes.
Yes. Exactly.
Nice.
Right.
Yeah. Yeah. Another question, like to go back to the kind of more high level, like one of the other things that the CLR has is like a lot of dynamic stuff, like reflection emit and dynamic loading, and now the DLR, things like that. That must also influence the garbage collection workload. And how do you deal with those things?
So what's new in V4 is the collectible types. So it turns out that in .NET, when you load a module, the code is not on the heap. The code is on special place, which is very similar to a normal C++ running runtime. And we can only unload a piece of code after if it's only executing for a given subdomain as opposed to a shared between subdomains, and when this subdomain has been terminated. Which is not granular enough for very dynamic type of computation such as the DLR. So we introduced in the new CLR v4 the notion of collectible types. So those are types that you produce at runtime, and if no one makes a reference to, so you essentially when you have code generated at runtime, how do you hold on to it? Usually you hold on to it by delegates. Essentially, delegates are an object view of the code. It's an object, but you can call on it. So when you lose your delegates and now this code is no longer referenced, then we can garbage collect it. So we had to add this, and it introduced more twists into the relationship between the runtime and the garbage collector. I mean, my upcoming talk at the PDC,
yes.
I have a diagram of what I consider the garbage collector, and for me the garbage collector is a very narrow thing, and it uses other services, but it's not responsible for stopping DE, for discovering routes. It's not responsible even for the helpers that assist in the garbage collection process or in the execution in the execution of the program. So we have a fairly strong separation in the CLR, functional separation between the garbage collector and the rest of the EE. So we had to add new interfaces in order to be able to collect the code. But you could see an evolution at some point where we would decide to have code more uniformly allocated on the heap, like a lot of scheme systems do that. Again, we are fighting against the old school and the new school. And the old school, which is, there are a lot of programs in Word and this thing, they are the old school. They spend a lot of time at build time to reason about a lot of what's the static view of their program, and they try to compile in the static view and make the static view static in the sense that it's not up for grab by anybody else. And we need to bridge the gap. The CLR has to be good at both. So if every piece of code is allocated on the GC heap, then it disregards or it disadvantages the static code that we would like to compile in the lab. In the future, we do have ambition to give programmers that want to have a static build of their code the tools to compile in their lab as opposed to on the client machine in Engine. But Engine is a tool that enables you to be more static, to have no jiting for the pieces that you pre-compiled. So in the future, we want to embrace kind of the ecosystem in both ways, be more static, and the ultimate static is have everything you can possibly do in your build lab be done there, and then the other one is everything is dynamically generated and it's reclaimable, and then so it's certainly a challenge to span the entire, but we believe we can do it. And certainly the collectible types is one way in the more dynamic space.
Yeah. So another challenge, I guess, must be, you mentioned a couple of times, the kind of more concurrency when we go to many core and things like that. So can you explain how that influences?
Right. So that's going to be the meat of the talks that I'm going to give. So I don't want to give you a spoiler.
You can make people kind of hungry to go to your talk.
But essentially, the big problems that we face is the fact that heaps are getting huge. Now memory is getting cheap. We have 64 bits, so the stupid 4 gig address space becomes a thing of the past. So I have personally seen customers having heaps in the 12 to 20 gigabyte range. That's one single heap for a single process, and collecting this, doing a full collection of it in a with no latency is certainly a big challenge, especially if we want to tidy it up and compact it. So that's a challenge that keep me awake at night, and I'll expose way in the future ways we are looking at it to solve this in the future.
So it doesn't that make sense then to do a copy and collector for when you have big heaps, or is that not?
It makes less and less sense because.
Well, but if your live data is small compared to your dead data,
then it makes sense to have an ephemeral collector, not copy.
Okay,
it's different. Yes. So ephemeral still makes a lot of sense. And that's actually why it's still usable. Essentially, people will try to make their generation 2 heap as stable as possible. Since we are adaptive, we actually know and take the hint when nothing much is happening, in particular it's not growing, and last full collection the survival rate was huge, then we say, okay, let's keep this for a while and not touch it. But when you have to touch it, then it is costly. So my area of investigation and ongoing work is actually to make large collection being unobtrusive as possible, and one of the innovation in the CLR v4 is about what we call background collection, which is the notion on being able to be engaged in a full collection, concurrent collection, and still be able to service Gen 0, Gen 1 collection at the same time. So you are able to just keep your heap tidy by compacting everything you can from the temporary data and still be engaged in a long, concurrent, low post time collection. And so this was enabled for the workstation GC. We are still in beta. Our early testing in-house say it's actually working really, really well. We would like to get more testing outside, but that's certainly something that we'll keep tuning. And then I would like to be able to port this onto the server GC, which has a lot of more challenges because the mechanisms that I'm using are not necessarily conducive to multiple processors, but that's something that we'll do in the future.
So one question I would have is sort of like in the managed world, the morphology of the heap. Is it like a relational database? So in other words, everything that's in the heap, you sort of are like they're related objects, and to some extent, as far as you're concerned.
Right.
So
the difference is that relational database have a fairly small number of object type, if you like. An object type, if you like, is the row of a relation. A row is an object, if you like. You can see that, and the column is the type. And there are very few of them. So what they do typically is they have one specialized storage per table, and the table is an entity on its own. In our world, we have thousands of type in even fairly modest heaps. So we essentially have instead a heap that is made of what I call segments, but it's just an internal facility. So, but essentially it's made of it's a linear thing, and inside you'll have next to each other objects, and these objects look very amorphous.
okay.
Certainly to the collector, the collector will have a uniform representation of them. To a collector, what it needs, we need to have a vtable entry that is used normally to do vtable calls, but also it contains the runtime type information. At the beginning of our vtable, we have few encoded fields that tell me how big the object is, and then we have a map, or hanging off of it too, we have a map that allows us to know within the object where the reference is, and that's it. So to the garbage collector, the notion of object is very primitive. Okay. It's something that has an entry to a section of the method table that the GC can understand, the rest couldn't care less about, and then it has objects that are side by side. It's actually a very interesting exercise that for a collector itself could host multiple type systems as long as this meta description is the same, and you could have interleaved objects that cannot talk to each other because they couldn't understand each other because they are from different type systems, but they would coexist on the heap nicely, and you wouldn't things would go well.
Interesting.
So to push that one a little bit further. So what like if you go if you move a little bit further, then you go to conservative collectors where you kind of don't even know the object layout, and you kind of just guess where the pointers are. Yeah. Is that something that well, you're laughing, but that's kind of people do that, right? Because you might
guess where the pointers are.
Yeah, you have to guess because you don't know.
Yeah, that's So if you look at why we have conservative collectors, we have conservative collectors because we have undisciplined code generation, essentially. By undisciplined, I mean we don't have access to where the objects are, and we don't have access to their map that tells us what. So the JScript collector that I wrote for our first JScript engine was conservative. And conservative, unfortunately, introduces a whole lot of inefficiencies because you have to hunt for pointers,
Yes. Yeah.
and also grief because pointers could even hide themselves. People can tear a pointer and say, "Oh, I'm smarter, so I'm going to encode a base pointer somewhere, and I'm encoding just some small int that are the offset within that base that will give essentially my pointers to my stores." And then the collector is
Yes.
just can't find these. So I believe that in the future it's easier to get even unmanaged programs to actually open up their stores and give out the maps of their object. I mean, I don't know if you remember in the old days. Well, not so much old days, but there was a object-oriented databases was
Yes.
came off, and one of the one that I have, a very good friend of mine studied, which is Object Store. Object Store was actually based on a technique to get the schema out of an unmanaged compiler, and then by understanding the schema, they would manage objects for the runtime, and will be able to swap the object in and out of a database. So for that, they needed the schema of the object, which is essentially a superset of what the garbage collector needs. But I believe that in the future, the direction that people will go is essentially try to get over the fact that they need to have essentially schematized data and then be able to find where their objects are.
Yeah, and in some sense, like debuggers and so on also need that kind of
Exactly,
information.
exactly.
So in order to
Right.
do something useful with your code,
Yes,
you
and
kind of
essentially-
already have that.
yes. And that's what Object Store
Yes.
was doing. They would
Yeah.
actually mine the PDBs to get the schema, because the schema is contained in the PDB.
So one question I would ask, since Eric and Patrick are in the same room, if you successfully convince everyone to start writing in functional programming,
Yeah.
which you've already talked about,
Yeah.
what would that mean for the evolution of the GC?
Well-
So let's say everyone just starts writing in a functional way.
So, well, I think that maybe the workloads might be different because things are not stack allocated, and the other thing is that closures often kind of have weird references to their environments which are different than normal
Right.
objects, because they are capturing local variables, and you have to be careful that it might be that your closure holds on to a couple of local variables but not to all.
Right.
So it's like
In a
closure
way,
can be
it's-
half dead.
Yeah, in a way, it's actually more. It's relies more on the garbage collector
Yes.
than
Yes.
normal programs
Yeah.
do.
Huh, interesting.
And this onus of doing this is more actually into the runtime system to give us, instead of giving stack view, give the roots
Yes.
of these closures, and then the closure needs to be described as object that we can traverse. In that case, then we'll do fine. I think the functional programming has, from what I've experienced, has a higher rate of object allocation and
Yes.
lower survival.
Yes.
And it's one thing that also they have a better knowledge of the object mutability, which would help. For example, the object allocator of the CLR will always guarantee to give out an object which is completely wiped out and completely clean. So we put 0 in all of the bytes of the object. But that costs, because we reclaim memory that was dirty, we have to clean it. And with functional programming, we actually could revert that to the compiler, and the compiler could say, give me dirty memory, because I am clean enough to know which part I'm going to build before I'm going to return this object. So the constructor takes ownership. When you are in the constructor, you haven't published your object yet. Nobody else can touch it. So essentially cleaning the object in the constructor or cleaning before giving it to the constructor are logically equivalent. It turns out that functional programming, usually the compilers have a better idea of better control over the execution of their constructors. So in that case, we would get efficiency, because right now we clear the object and then it gets overwritten very quickly. Hopefully it's still in the cache, but it's still double duty. So we would gain efficiency if we had a better contract with the functional language compiler. So that's one area.
Yeah, so that's kind of an interesting thought, because, like, in some sense, the way I look at it, you're nulling out these things to make sure that when you get a null pointer, it's really a null pointer.
Right, and
right?
also
and it's not something that was there before.
And even for numeric fields, we don't want to have undefined numeric fields.
Yeah, but would it help then, like, instead of kind of going all the way to immutable types and so on, to have like the notion of a non-null type? Would that, because now you kind of know that this type will never be null, so then when you
if we had the notion of essentially the constructor will always give it a known value, therefore we don't have and so that would be helpful, but the contract has to be at the entire object, not at the field level, because essentially for us it's as expensive to since we use SSE-like instructions to clear. You know,
so it's like either or or not.
Right, exactly, right. Yeah, clearing 20% of the object wouldn't be profitable to us.
And so one interesting thing there is that you talked about this before, because the CLR is a multi-language runtime. These things now also make it kind of hard to have the same contracts, hold across languages.
Right, but this one, for example, we could specialize the contract. We could have regions of memory that we clear and which one we don't clear, and then we give out based on we have two different helpers. We have the give me clean object helper, and then give me the non-clean helper, and we will give them out from two different pockets of memory. So that's one thing that could be done.
And so, since we're kind of also at the PDC, we're in the panel about languages. So, is there any obviously we talked about that. There's like a relationship between languages and the garbage collector. Like if your language has certain guarantees. Do you think that we can design our languages better to make your work easier? Or do you think that that the distance is kind of far enough?
So as far as if we talk about memory management, we've looked at some construct that would help interop between managed and unmanaged. And that's part of something that we are exploring for the next version of our programming languages. Right now, there is a significant gap between the two, and we don't trust an unmanaged memory coming up. So the OS, for example, will give us only unmanaged memory, and it has certain guarantees of its lifetime. When it makes a call, it's guaranteed that this memory will be around until you return from the call, for example, when it makes a call back. And yet we don't really take advantage of it in our current model. We copy this unmanaged memory onto a view that is a managed view. We just make a straight copy, and then the managed view looks at it, even though it doesn't necessarily need to, it can be just a read-only thing. and then if it's a writable, then we'll write it back at the end. And so if we had better language construct, we could actually express the cast of this memory onto a type, a reference type that is in manage but doesn't require copy.
Okay.
So for example, if you could obtain a reference off of a buffer to an int, you say that's my reference to an int, and then the compiler will make sure you can't actually store this reference anywhere. You can just use it on during your execution of your current program. You can still peek at that memory without copying it, therefore being much more efficient. And then when you return that you forgot about this memory. So these kind of things we are definitely looking at.
Okay, so it seems that you will have many more years of work ahead of you. It's seems that there's more problems coming up. So, well, I'm really looking forward to listening to your talk and having you on the panel. And yes, and
also learning about the Holy Grail of GC.
Yes.
Which you want to save until the PDC.
Right. Yes.
Because you want. This is people are going to love this talk, but they're going to actually really want to go. And when you go see his talk at the PDC, hopefully you're watching this right now. Have some questions for Patrick. I mean, you're going to get, this is the guy. This is the godfather of the CLR's GC, man. So make sure you have some good questions.
Yep.
And it's going to be fun to watch this. Take care. See you down at PDC.
Yep.
Thanks.
Well, thanks a lot. And see you at the PDC.
Great shirt, Erik.
Yeah, especially this is like a web, right? So it's like it's the memory that Patrick is collecting.
Hey, that's what the heap looks like.
Yes, exactly.
Cheers.
All right.